Okay, everyone, welcome to our Tuesday.
Right.
Let me repeat the things I just said. Okay. All right. So first, before we get started, your classmates, Alexis, have a very important announcement. Okay. Here we go, Alexis.
Hi everyone. Hope everyone is doing well given the pandemic. I'm here to kind of talk about the ballot bowl. Santa Monica College registered recently to this statewide competition among all community colleges to see who registers the most voters. Um, we've been doing a lot of work and a lot of students have been sharing the links and everything. And we're really excited to announce that we're in second place statewide. But we could do better and we really want to beat Riverside City College. So please register to vote. We're a few, and if we win, we get bragging rights, we get a trophy, and we get to be number one. And if you haven't registered to vote, you can do so at this link, and it is different. This is a special link. It is registered to vote.ca.gov, and it's very important to put this unique ending because this special link will ask, the only difference is that it will ask you what college do you attend, and that's how we get points in the statewide competition. Um, Very important, October 19, this upcoming Monday, I believe, is the deadline to register to vote in California to receive a mail-in ballot. You can register to vote on the day of the election or at a polling center that is called conditional registration, but you must be in person. The October 19th deadline is to get a ballot by mail and then decide whether you want to mail it back, whether you want to drop it off, whether you want to deliver it in person or have someone deliver it for you. So there's many options, and I know it may seem a bit overwhelming, confusing, and that's why we've put together this special link. SMC, the Civic Engagement Committee, put up this webpage, smc.edu/civic engagement, if you want to learn more about voting, about tracking your ballot, about all of these important resources about civic engagement opportunities, etc. And this link I love, ballotready.org, is a link where you just put your address and it tells you how you can vote, your deadlines, what's on your ballot, very nonpartisan information and objective, and you get everything you need to know to make an informed and early vote, which is really important. And yeah, that's all. So take a screenshot of that. I'll send it to the chat, and please register to vote. It's coming up. Thank you.
I have a question, Alex.
Yes,
Okay, so who will be eligible to vote?
to vote. Okay, so in California, it is all citizens above the age of 18. In terms of formerly incarcerated people in California, you do have the right to vote, although there are some circumstances that I recommend you check out at registeredtovote.ca.gov. If you're not eligible to vote, there's still ways to be civically engaged. You can be informed, get out the vote, and fact check people. I'm not eligible to vote, but I'm here presenting. So again, there's multiple opportunities to become civically engaged.
Exactly. Second question.
Yes.
Will you be able to share the presentation with our class?
Yes, I
Okay.
will. I'll send that.
Okay, so maybe you can send that presentation to me and I can include that into my video link, this
That would be
class
great.
video link, and people can check. And on Thursday, I will also save like 1 minute for you to remind people to do that again.
Okay, thank you so much.
I think that's coming Monday, right?
Yes, yes, very soon. So very important. Thank you
Yeah.
so much.
Yeah. So this is a very important thing. I'm not eligible because I'm not a citizen, but I encourage all of you to uh, uh, participate, okay, into this very important thing, okay, in determining our future at least in the next 4 years, right?
Yes. And a lot of ballot measures, a lot of laws, a lot of state councils. There's a lot
Yes.
more to the ballot.
And also, if you choose to drop off this morning when I listened to NPR, there's a lot of private drop off box made by people. Make sure you drop off your mail, your vote into the right mailbox.
Yes.
Okay. All right, so any other questions for Alex? Okay, thank you, Alexis.
Thank you.
Okay, so let's get started our class. Okay, let me share the screen with you. Okay, so, oh, there's a chat. Okay, all right. Okay, so this week we will officially kick off this water in atmosphere, but we sort of like finished half already last week on Thursday when I was in Dubai. Here are those modules, and you can see I published this lab already. So later at the end of today's meeting, okay, let me point out some of you as a group leader, okay, and then you can sign up. If we have time, you can briefly chat, but we will reserve Thursday's meeting, okay, focus on this assignment. Okay, and today let's focus on finish my lecture presentation for water in atmosphere. Okay. All right. So let's click on this. Let's see a chat. Oh, okay. Good. Alexis shared the things in our chat box. You shared. Okay. So make sure you copied it. Okay. All right. So click on this link. Oh, actually, I have that happen here. Sorry. This one. Oh, no. Okay. Sorry, let me reshare just the screen. Okay. All right. So, water in atmosphere. I believe last time we went over the specific humidity, different measurement, how to measure the air humidity, right? Okay, any questions on this? No, you know the difference between how much and how saturated, right? Why we have this how saturated, this concept coming in? Because air have certain ability, right? If you fix the temperature, given temperature, air can only hold certain amount of water vapor, right? So that is, then we can use this capacity, okay, as the denominator, right? And then to compare how close you are to this saturation. So let me see where it is. How close that you are to this saturation stage. So that is how full the air is. Okay, when the air is totally full of water, well, you will see what? Condensation. Okay, so that is why this concept is very important. So you can see this chart, okay, like last time Alexis asked this question, okay, how do we know there's actually a fixed relationship between temperature and the maximum, the saturation, okay, amount of water vapor the air can hold? So you can look it up in your lab 3, you actually have a lookup table, okay, certain temperature, you have maximum amount, okay. All right, so you can see this concept actually applied every day when you see the daily change of our relative humidity and temperature. Okay, so you can see that is in the course of the day from 5 p.m. the previous day and to 5 a.m. okay, in the morning. So you can see in the late afternoon when the temperature is high, let me annotate. When the temperature is high, our relative humidity relative low. Okay, so that's why at noon sometimes you feel thirsty, right? You feel a little bit dry, right? So that is relative humidity is low. So basically the air is hungry for water, thirsty. But you can see when you're approaching to, after sunset, okay, maybe 6 p.m. right here, right? When the temperature goes down, okay, you can see our relative humidity goes up, right? They have this opposite changing direction, the trend, okay? So that is basically warm air can hold more water, cold air hold less. water. And also in the morning, you see the relative humidity is so high. Okay, it's very, very, oh, I'm sorry, this is the relative humidity. Relative humidity is high. If the air happen to be full, well, you will see fog. You will see our marine layer. Like this morning, I ran to the beach. I see the marine layer. They are moving up to our Santa Monica Mountains. It's just so beautiful. That is the thing I was missing when I was in Dubai and in my hometown. We don't have that because relatively dry. Okay. And there is a very important concept. It's called dew point. So can anyone remind me what is dew point temperature?
Is dew point the temperature that you start to see water?
Exactly. You start to see condensation, water droplet. Exactly. Okay. So you can see if you fix the amount of water, actual amount in the air, okay, you don't touch it, but you decrease the temperature of the air, then you also decrease what? The capacity for the air to hold the water, right? So you basically shrink the capacity. So the same amount of water vapor eventually will condense out, become water droplet. That is very exciting, very beautiful. That is your cloud in the sky. Okay, so here, let me clean my drawings. Okay, let's go to the next slide to study the cloud. Okay, oh, here. Okay, so this slide is very important. Okay, I want people to know you can tell this story, how the cloud is formed. Okay, cloud formation process require these three things. Okay, the air parcel, this pocket of air must be able to rise. If it just stay at the ground, they never get the chance to form the cloud because they never saturated, right? If you don't add water in it, or if you don't cool it just at the ground. Okay, so this air bubble need to rise. And then in this process, air cools down, right? In troposphere, the air, when you go up, elevation increases, your temperature drop. There's actually another process called adiabatic cooling. Later, we will learn that in the next slide. Can also cool down the air, okay? Basically, the air expand, okay? Adiabatic cooling. Anyways, temperature goes down and you will reach the dew point temperature at certain level. For example, in this little chart, figure here, that will be here. Okay, so that's why all the cloud, or most type of the cloud, you have this very flat base. That is actually the air can only rising to this level, okay, so that they can condense. You will see the cloud. We call that lifting condensation level. Lifting condensation level. At this level, air temperature is at the dew point temperature. Okay, temperature is at the dew point temperature. So you will see the condensation. Okay, in addition to that, you also need constant condensation nuclei. Okay, so well, that's the physics of our water. You need a condensation nuclei for our water to grab those surface and then to form the chain. They hand in hand to form this hydrogen bond, and they can condense out, become liquid. Okay, otherwise they can't. Okay, so that is a process. Maybe next morning, when you do your meditation, okay, remind yourself this process. Air is rising, they're cooling down, they will reach to the dew point temperature, and then you will see the water vapor condense out to form the cloud. Okay, so that is a cloud formation process. Okay, any questions before I move forward?
I didn't really understand the nuclei. Is it like the hydrogen bonds, or?
No, it's some physical, it's some solid or liquid surface like a dust, like a volcanic ash. Okay, those physical surface our water droplet can merge up, can grab up, you know? And then when you have one water droplet, okay, attached to it, and then other droplet will use that hydrogen bond to, you know, form that chain. And then you will see liquid. You know, liquid and gas, their difference is they have this slightly tighter hydrogen bond, right? They hand in hand, but gas is, you know, everywhere, they're separated. If you don't have this, like super pure water, if you put it in a fridge, actually they won't freeze. You won't see ice because that's super cooled water. Temperature can be below 0 degrees Celsius, but still in liquid because they don't have this condensation nuclei. Okay, yeah. I think I watched a video to show you this experiment. Let me find that one and share with the class. Super cool. All right, any other questions?
I have a quick question.
Sure, yeah.
So once it gets to the LCL, the air is colder up there, and that's why it stays as the liquid in the cloud, or the gas.
No, lifting, condensation level. Okay.
I'm just a little confused about that part.
Air temperature equals to dew point temperature.
Okay.
Okay.
So
here, yes. So air temperature is cool enough to make condensation happen. Air temperature is cool enough to become saturated.
Okay.
And then you will see those, you know, little droplet condense out, like being squeezed out, you know, but they're too small. They cannot, you know, falling down to the ground. They will just suspend it there and you will see the cloud. Yep.
Makes sense.
Very good. Very good. Okay. Oh, of course, if the air can keep rising at this place, okay, and you will see more and more water droplet condense out. So that's why your cloud can become so large and so tall. Okay, so here we go. Let me clear my drawings and let's go to the next slide. Okay, so different types of cloud. Okay, you will see this, well, you see this one a lot in Santa Monica, especially in winter when we have more moisture, right? We call that cirrus cloud. Cirrus means feather-like. It's like feathers, right? Okay, so, and also a fun fact is they're very high. They're very high up sky, and mainly contains the ice crystals because they're up there. They're so cold, they become the ice already. Okay, cirrus cloud, very wispy cloud. Okay, and you probably have these type of cloud, like a cotton ball, like a cauliflower, a broccoli, right, in the sky. So we call that cumulus cloud. So how you form the cumulus cloud? Exactly what we just talked about it in a previous slide. You basically have the air rising, okay? And to this lifting condensation level, temperature cool enough, you see condensation. And the air can continue rising and to form this ball-like, okay? But if they go too crazy, you will see this tower cloud. We call that cumulonimbus cloud. Means you have a lot of water vapor to condense out, right? Nimbus, this part, nimbus means moisture laden. Okay, I think it's in Spanish or Latinx. I don't know. But it means moisture laden. So you can see you have a lot of water to condense out and the air can keep rising. So you will grow very tall cloud, okay? Sometimes you will see this cloud in the late spring or in the spring, okay, when we have, you know, in LA, I mean, but in other parts of the world, like in Philippines or Singapore, well, that is every day actually because they're so moist. Oh, hi, right? Hi. Okay, so that is a cumulus. You can see that's ball shape like, right? And cirrus, that's like feather-like, okay, very wispy cloud. You also have this type of cloud, like a sheet, okay, like your baking sheet, right? Stratus cloud, we call them stratus cloud because stratus means layers, okay, like pancakes, right? They are horizontally developed, not vertically developed. Okay, so this is a stratus cloud. Then you probably want to ask how this one formed, right? I know the areas they want to rise, but why they stay, horizontally? Very, very good question. Okay, very good question. If you see this stratus cloud, that means beneath it, the entire chunk of air, they rise together. Not like those bubbles, here beneath this cumulus cloud, you probably have the air parcel. We call that parcel, like the parcel you send to USPS, right? It's called cumulus cloud. It's like a bubble, like a pocket. They just this individual pocket rise. But here you have the entire layer of air rising up and they rise together. Then you will have this, horizontal shape, stratus shape, okay, cloud. Okay, so that is the three basics type of the cloud. Okay, wispy like, that is the cirrus. Okay, layers, it's a stratus. Okay, and like a ball shape like, they are accumulated together, accumulated together, we call that cumulus cloud. Okay, questions about the three basic shapes, basically I'm talking about here. Good. Okay, you should be able to identify different type of cloud. Okay. And also we have another way, but it's, we very rare use it. Okay. Well, I mean, singly use the altitude because it's so hard to measure the altitude. Okay. We have low, middle, high, and vertical developed. Okay. So you can see, well, you can combine the altitude and shape together. So for example, you have this autocumulus, right? So those cotton ball just in the middle level, okay? And you have those autostratus, those layers, they a little bit high, right? It's in the middle cloud, okay? But mainly more interesting way actually to use the shape. All right, here we go. Okay, let me clear the
Professor, does rain only occur in stratus clouds?
Say that again.
Does rain only occur in stratus clouds?
No, sometimes cumulus like this one can also give you the thunderstorm, right? But I get your point, Abraham. When you see the stratus cloud, you will see very cloudy day. They overcast the entire sky, right?
Okay, got it.
Yes.
Thank you.
So when you see the precipitation, well, your air need to have a lot of moisture in it. And the water can keep condensing out, and then the water droplet can become so heavy so that they can fall. Okay, so not necessarily, but you have a point. This cirrus cloud never give us the precipitation, never give us rain. They're just too high. Okay. All right, very good question. All right, then there's a very important question actually, okay? Different way to lift our air, okay? So you can see this one is, the first one, okay? Convection lifting. Let me move our chat box and let me draw, okay? This one, convective uplift. Okay, what is convective? Convectional oven, right? So you will have this pocket of air, it's heated up. Warm air rises, cold air sinks. That is so-called convection. convection. Okay, so when the air become warm, they just rise, right? And another way is to use our mountains. Okay, I think last time we talked about it, you know, when the sea breezes blow against our Santa Monica Mountain on the Malibu side, right? When the air is forced up, you will see a lot of fog, cloud on our side of the mountain. But if you go to the valley, they usually very dry, right? So this is another phenomenon we're going to talk about later. It's called rain shadow, okay? So, but mountain can push our air up. Another one is frontal. Frontal is on the next slide, okay? So you can see we have very, very dense, let me clear the drawings. We have very dense cold air. It's just like a rock, like our mountains. But when you have the warm air blow against this cold air, warm air will be forced rising, okay? So that is frontal uplift, okay? The last but not least, this is the convergent uplift. What is convergent? You have this low pressure. This low pressure is just like a vacuum. Your vacuum machine, you know, they can suck the air in. But the air cannot stay here. Air will be squeezed up, okay, like a water fountain. And then air rising when temperature and, you know, the moisture is ready, you will see cloud. This basically is our hurricanes. You can see this year is also a very crazy hurricane season, right? Okay, so this is the hurricane cloud, how they was formed. Okay, any questions on the 4 lifting mechanism? Pretty easy, right? Okay, so in our area, I would say mountains play a huge role. Okay, we are not very much affected by France. Okay, we actually have very lack of France every year. Okay, and also yeah, we don't have much low pressure. Mountains play a big role. Okay. All right. Okay. So stability. I have this very cute balloon to share with you because the air in it is not stable. You have these events actually every year. I think somewhere between San Diego and LA. I forgot the location, but they have this competition which balloon is cuter, you know. But the air in it is not stable. Why I say that? Because if you release the rope here, well, maybe the hot air balloon will rise, right? So this is the concept of this unstable air parcel, okay? So unstable air parcel is warmer inside than the, you know, surrounding air, okay? Than the air surrounding it. So I'm talking about the air here, air here, air here, the environment. Air inside this balloon is warmer than less dense, right? So they will rise. So if you have this type of air parcel in your cloud, the air want to rise, then that air parcel is not stable, okay? On the flip side, okay, if the air is stable, why we say it's stable? It can stay there, right? Why they have to stay there? Because they're not warm enough. They're even colder than the outside temperature, outside environmental temperature, okay, surrounding air. So you can see here, how you decide, how you determine an air parcel is stable or not stable. Very easy. You just compare the temperature, right? If the inside temperature is warmer than the surrounding air, unstable. If the inside air temperature is cooler than the outside, right? Okay, then it's stable. It's stable. You just compare the temperature. Does that make sense? Okay. So, well, then in your lab, how you calculate it, right? Okay. So here's the thing, guys. You need to remember, as long as you go up, the temperature for the environment, let me use TE here, will drop, okay? Because in the troposphere, right? The air inside your air parcel, let me use TA, okay, will also drop, okay? Will also drop, but they use different rate. They drop with different speed, okay? So that is the thing you need to figure out, okay? When you determine the unstable air or stable air, okay? For the environment, you have this rate called environmental lapse rate. Environmental lapse, collapse, right? They drop. Environmental lapse rate. This one, global average, that is 6 degrees Celsius per 1,000 meter. Okay, 6 degrees Celsius per 1,000 meter. But global average, guys, this rate actually is very dynamic. Depends on where you are, depends on when you measure it. Every day, this guy, like our moisture, change a lot. Okay, change a lot. But for our air in it, okay, the air inside our balloon, this rate, you just have two options. Okay, for this one, the lapse rate. Let me use text. Lapse rate, okay, inside air parcel. Okay, you just have two options. Number one, if the air inside is not saturated, so relative humidity is less than 100%. We call that dry air. Okay, we call that dry air. This rate will be very fast. Okay, and then if the air inside is moist, okay, or we'd better say it's saturated. Excuse me, my hand drawing here. Okay, saturated. Okay, then that rate will be slower. Okay, so that is the thing you need to pick up. So here you can see you need to take a look at the air is moist or air is dry. If you see, oh, relative humidity in it is 100%, then you use the moist one. Otherwise, you use the dry one. Okay? All right, remember my rules, okay? Number one, just very simple three rules, okay? Number one, both temperature, inside, outside, they will decrease when you go up, okay? Always subtract your numbers, okay? For the outside, you use this temperature, you use this temperature, environmental lapse rate, okay? Global average, 6, but depends on where you are, okay? You can look it up, by the way. And inside temperature, you have two choices, dry or moist, okay? If the air is saturated, you use moist. If not saturated, use dry. Simple? Okay. All right, we will practice, okay? But I want you to be clear about the rules. All right. Okay, so global average about like 6.5 per 100 meter, okay, or 3.5, I think, 3.5, 3.6 every Fahrenheit every 1,000 feet, okay? But you can see inside air temperature is different, right? That's depends on your moisture level. Okay, so you can see, let me skip this one first. Okay, here. So you can see if the air is unsaturated, it's dry, this is the rate you're going to use. This one, we call that DALR, or dry adiabatic lapse rate. Okay, dry adiabatic lapse rate. Let me explain what is adiabatic later using the previous slide. Okay, if the air is saturated or moist, we use this SALR. Okay, it's 6 per 1,000 meter, or 3.3 Fahrenheit every 1,000 feet. Okay, it's called saturated adiabatic lapse rate. Okay. All right, so here, that is the two rates you're going to use. Okay, and this calculation. Before we move forward to calculate our air temperature and to determine whether it's stable or not stable, let me introduce you this adiabatic process. Okay, this adiabatic process is very interesting, very weird. It sounds very weird. Okay, you know, let me ask you this question: how you get warmer or cooler? For example, on the Earth's surface, how the Earth's surface get warmer or cooler?
It gets warmer by absorbing the sun's heat rays.
Exactly, Professor Maggie, you get it, right? That is a process. You need to absorb energy, right? But can you imagine you can warm up the air without absorbing energy? Sounds weird, right? Okay, you actually can increase the temperature of your air by compressing it without absorbing any extra energy. Okay, if you bike, oh, I have my pump here, finally. You probably have this, right? Your bike pump, okay? So if you pump your bike vigorously like this, okay? Do some workout. Later, you will feel this tube become very hot. Do you have the experience? I bike a lot. I need to pump my bike a lot. So sometimes I feel, oh, this tube become very, very hot. Okay, or you have your cookie presser or something, you can practice. Okay. Okay, so what I'm doing here, you can see I'm pressing the air, right? When pressing air, I'm forcing the air into my tire, my bike tire, right? I basically squeeze them. By squeezing them, actually I speed up the movement of the air molecules in this tube. Make sense? I push them moving forward, but they don't want to go. They're lazy, but they actually eventually will speed up. And then, temperature is a measurement of how fast air moves. So if you force the air, let me go here. Okay. Oh, compression is here. Okay. You can see. Let me move here. If you see the air going down, okay, and then you become smaller, you squeeze it, the air molecules in it will become very fast. They're moving very fast. Once they move very fast, the temperature will rise. So you can see now I'm not using any extra outside solar energy or other energy. I just, use my pressure, right, to force the air moving faster. So this process can only happen when the air is descending, because the air pressure close to the Earth's surface is higher than up there in the sky, right? So basically when the air passes descending, the surrounding pressure will become bigger and bigger, and just like me squeeze my pump, They will squeeze the air parcel, become smaller, and speed the air molecules in it. And then you will measure a higher temperature. Okay, as opposed to the air is rising like this, right? The air will expand. Okay, they have more room, and no one squeeze them, right? No one push them. They will lazy. They will become lazy, right? They will just stay there, moving slowly, and then temperature decreases. This can only happen when you have the rising air, Okay, so let me pause here. Any questions about this adiabatic process?
When does this process happen? Is it like at a special circumstance, or is it like always happening?
Always happening.
Okay.
I should say, as long as, for example, this adiabatic cooling, as long as you have the air rise, it's always happening.
Okay.
Because pressure is always there, right? So this lifting, different lifting mechanism, like a convectional lifting, convective lifting, orographic lifting. For example, our mountains, you have a mountains right here. When the mountain push the air rise, this process happening.
Okay.
But when the air descending on the other side, adiabatic warming will happen.
Okay. Oh, that makes sense.
So that's why in the valley it's so hot.
Right.
Guys, turn your fans on, turn your air conditioner on. In the next 5 days will be super hot, especially when you're far away from the ocean. Okay, any other questions? All right, okay, very good, okay. Okay, then let's save this calculation on Thursday. Okay, there will be a big question in your lab. Okay, so when you go up, determine the temperature, determine the stability. Okay. All right, let's see. Then we pretty much finished this one already, right? So that is lifting condensation level. It's a level when you see the air become saturated, right? So you can see, let me remind you again, the air parcel moving up, right? Temperature will decrease by adiabatic cooling, also by, losing the energy to the surrounding air, right? But anyways, you go to this level, it's cool enough. You see the dew point temperature, right? You see the dew point temperature, and then you will see the cloud. Okay, and above the LCL, the parcel continue cooling as it rises. The air remains saturated, and because the air temperature is equal to the dew point. Because, yeah, so basically the temperature is dropping and dew point temperature is, decreasing, and then you will see more cloud. Okay. Okay, so, all right, here we go. Let's see those beautiful clouds. Okay, let's see those beautiful clouds. This one, I think I downloaded this image in Brazil. Okay, so you can tell by just what we just learned. Okay, the air, I say, rising up this side of the mountain. Do you agree? Yes, yes, because this side is nothing, right? This air must be this air parcel. Okay, let me go back. Okay, rising against the mountain from this side of the ocean. Okay, and then they form the cloud. Okay, lifting condensation level is right here. Okay, but when they move to the other side of the mountain, they will sink. They will sink, right? So that's why here you don't see any cloud. What is happening? Air here, right? And when they descending, they become smaller and smaller. Adiabatic warming. So, well, when you reach the you can reach the dew point temperature on this side, but since you increase the temperature on the other side, you never get saturated, right? So same thing happening in the picture here, okay? You can see those clouds when they descending against the mountain, along the mountainside. Because they got compressed, they become warmer and warmer. They have more and more capacity to hold the moisture, right? Okay, they never get saturated. So you can see those clouds, they form on the other side of the mountain, but dissipating on this side of the mountain. Okay, so you can see mountain actually play a huge role in terms of cloud formation, right? Okay, and also the moisture level in your area, okay, in your area. Let me clear the drawings. Okay, so then there's another lab question we are going to work on on Thursday, okay? We are going to determine, to calculate at which level you start seeing cloud, how much rain you are going to see on this side of the mountain, and what's the temperature when they get to the other side of the mountain, okay? But here, let's just, compare the two sides of the mountain. Okay, let me annotate. You can see I start with 22 on this side of the mountain, right? But when I get another side of the mountain, same level, my temperature becomes 30, right? And you can see this side is very moist air. You see very green, the vegetation, but on the other side is the desert, right? The air also becomes very, very dry because it loses tons of moisture on this side already. Okay, and of course, temperature is high, you see more evaporation on this side. Okay, so anyways, let me clear the drawings. Okay, so this is the effect, we call that rain shadow, which actually very common on our Earth surface. Okay, well, here, Hawaii. Since I'm showing you Hawaii, let's talk about Hawaii. Okay, my favorite place. Big Island. This is a big island. You can see now, you see the annual rainfall. Okay, Hilo is here. Okay, Kona is somewhere here, I think. Okay, so you can see on the same island, it's very small island. Not that small, but you got my idea. Okay, this side, Hilo get tons of the rain every day. When I was there, it rains every day. Okay, and I had a friend over there, she lives there. She told me she never water her garden. And because of volcanoes, they're so, so rich in many microbes, in their minerals in their soil. She never put, fertilizer in her garden. She just throw the seeds and they just grow, That make me want to move to Hawaii. Okay, but anyways, you can see on this side of the mountain, these are volcanoes. Okay, Mauna Loa, Mauna Kea. Okay, volcanoes right here. You can see against the mountain on the windward side. We call that windward. Windward. Okay, windward side of the mountain, you see a lot of moisture. Okay, but on the other side, we call that leeward. Leeward side of the mountain is very dry. It's very dry. Okay, and it's applied to all the islands in Hawaii. You can see Maui, same thing. Molokai, the same thing. Oahu, same thing. Believe it or not, Honolulu. You know Honolulu, right? It's right here. Okay, Honolulu. If I ask you what kind of climate you expect in Honolulu, you probably say like a rainforest, very moist. No, big fat no. Okay, actually they are dry climate like us. Can you believe that? They just close to the ocean. That is just because they are on the other side of the mountain. Okay, the wind coming from this direction, that's our trade wind. Okay, trade wind. Okay, and those are the mountains in Oahu, on Oahu Island. Okay, you can see Honolulu actually is a dry climate. Okay.
I have a question.
Yes.
Does the wind direction ever change?
This one never change. We call that trade wind. But for our local area, the predominant wind is from the west, from our ocean. Okay, but of course, occasionally you will see the local scale, the wind. So that's why when we learn the wind, we have different scales. Like our sea breezes, land breezes, that probably just, apply to this local LA area, but not for all the places, right? Yes, very good question, Nico. And here, this is another very important place you see this rain shadow effect. Okay, these are Andes Mountains. Okay, up there is Peru. Okay, I see Cusco here. Okay, Lake Titicaca here, and this is your Chile. Okay, well, Chile is on the leeward side of Andes Mountains. Okay, their trade wind coming from this way. Okay, coming from this way. So you can see Brazil, Argentina, they have very good amount of precipitation, right? Brazil, you even have the rainforest, Amazon, right? But Chile, this part, this Atacama Desert, it's the driest place on the earth, guys. Guess the last time they see the last rain droplet is how many years ago? Let me tell you. You're ready for this? 50. Imagine there's a kid, okay, 8 years old. In his whole life, never see a drop of rain. That is the driest place on the earth. Okay, because of this rain shadow, also because you have this cold ocean currents. Okay, we will learn currents later when we learn ocean, but the cold water here, like our ocean, okay, California cold ocean currents, make the air very stable. Air is cool, basically. Okay, air is cool. Air can only want to stay there, it never want to rise. So you sort of like this double dry effect. Okay, so this is the driest place on the earth. Okay, very interesting. In our local area, you have the experience. I believe you've been to Vegas, right? If you drive when you pass the mountains, right? All of a sudden, the landscape just changed. You see this side, LA, this side, we're okay, right? You can still see the color called green. But on the other side, no, just the desert, right? Okay, same thing, because our predominant wind is from ocean, okay? Below, again, San Gabriel Mountain, but to the other side, Vegas will be very dry. Okay, also why, let me share the screen with you. Let me clear my drawings. Okay. I think this is the last slide. Yes. Okay, cloud formation, precipitation. Okay, let me quickly share with you satellites. Okay, go to Google. Okay, let's as a geographer, we always switch to the satellite so we can see the vegetation. Okay, so you can see immediately you see this rain shadow effect everywhere. Okay, you can see here Malibu, this side of the Santa Monica Mountain is very, very moist, right? But valley is very dry. Okay, valley is very dry. Okay, so let me move. Okay, you see Vegas. Okay, let me zoom up. Okay, you can see this side of our Angeles National Forest is very moist, but on the other side, desert, right? If you keep zooming out, okay, to see the California, the border between California and Nevada. Why Nevada is so dry, guys? Because our mountain, okay? Because our Sierra Nevada mountain, okay? We have the wind blow this way, okay? So it's everywhere. And if you've ever been to Seattle, you know, Seattle rain a lot. You even have a movie, Sleepless in Seattle, right? You know, Tom Hanks carry umbrellas every day, right? Okay, why? Because they have tons of mountains here. Okay, they are volcanic mountains. Okay, so when the air is forced against our mountain, okay, they you know, drop down a lot of moisture on this side, but all of a sudden on the other side, like this Moses Lake, it's super dry. Okay, it's super dry. Okay, so you can see this rain shadow is everywhere. Let me pause. Any questions? Are we good? Okay, all right, very good. Okay, one place you just remind me, in India, the same thing. You can see why India, you have, you know, so many types of rice. When I was in Dubai, I actually enjoyed the Indian food. Multiple types of rice. Why they're so moist down here? One thing is monsoon. The other one is Himalaya mountains. You can see Nepal, this side is very, very moist. But if you go to Tibet, it's dry, actually. It's very dry. Okay? All right. Okay, so last slide. Okay. Last slide is different type of precipitation. Okay, very simple actually. What type of precipitation you will have actually depends on your cloud. Okay, what depends on your cloud? Depends on the temperature of your cloud. If you have this warm cloud, you know, the water just can't stay in the liquid phase. Okay, so the precipitation formation basically is you have those two droplets. You know, when they come closer, okay, they will boop, merge into one water droplet. Okay, and you have more and more water droplet, they can merge together. So this process, we call that collision and coalescence process. Okay, collision and coalescence process. And if the cloud is so cold, okay, like in Alaska, okay, or in Antarctica or Arctic, right? Okay, you have this ice crystal process. Okay, what is ice crystal process? Well, if you now, okay, pick up the ice cube in your fridge, okay, you will feel that ice cube is very sticky to your hand, right? It's very sticky to your hand. Sometimes you cannot get rid of it. Okay, why? Here's the thing, guys. Ice, water droplet, those two things. Okay, if I'm a water droplet, I'm a water vapor. Okay, I prefer to condense to the ice cube, not the liquid water. Okay, liquid water is not attractive to me. Okay, I like ice crystals. Okay, because physically, ice crystals is easier to, you know, attach water vapor in it. Okay, they basically will prefer to attach the ice first. So that's the ice crystal process. You know, I just make the very complex story very simple. Okay, so when you have both ice crystals and liquid droplet of water, they coexist in your cloud. Our water vapor will prefer to the ice cubes. Okay, so you will form what? You will form snow. Yes, you will form snow. You will form the solid phase, solid precipitation. So snow, you know, the what's called the freezing rain. Okay, so you will have the ice crystals in it. Okay, so that is depends on the temperature of your cloud. Okay, and well, but don't forget, never be so simple. The cloud with a range of temperature. So for example, in this super tall cloud, okay? At the bottom, maybe this collision coalescence dominant, but when you go up there, you will have very cold temperature, then this ice crystal process dominant. So that's why, you know, sometimes in those thunderstorms, you know, you will have the ice ball, right? Hail, that's the word I was looking for. Hail coming down. So you have both process happening in your cloud, okay? Which actually is a very, very violent type of weather event, okay? We want to watch out, especially you are going to have a plane to catch. Okay, so I think that's all the things we're going to learn in this presentation. Any questions before I let you go? We good? Okay, so email me your questions when you study, when you go through the concept and also our study guide. Okay, and today, oh, one more thing. Who want to be the group leader this time for Thursday? Jean, you're scary. Do you want me to assign the group leader again this time? Yes? Okay, then that is the power of teacher. Okay. So let me just, again, like last time, I will assign some of you like as a group leader, and the rest of you will, you know, sign up for different groups. And then we can work on the lab together on Thursday, okay? All right, wish you a happy Tuesday and productive and happy week. Don't forget to register to vote, okay? I will see you on Thursday. Okay,
Thank you,
bye.
Professor.
Thank you.
Bye.
Thank you.
Hi,
Bye.
Professor.
Bye. Stop share.